Good morning student. Previous class I discussed about the buffer solution, types of buffer solution, and also I discussed about the buffer capacity and some problem related to the buffer capacity. Now I am going to discuss about the Henderson's equation. At first I will discuss about the Henderson equation for acidic buffer solution. We know that acidic buffer solution is made by weak acid and it's a salt of strong base. Let us consider an acidic buffer solution Ha plus Ab. Here Ha is the weak acid and Ab is its a salt of strong base. When the weak acid Ha undergoes ionization, then what will happen? It gives H plus ion and A minus ion. So here I can write Ha gives H plus A minus. Now I can apply the law of chemical equilibrium. According to the law of chemical equilibrium, I can write K equal to concentration of H plus into concentration of A minus divided by concentration of Ha. Here K is the equilibrium constant for acid. Here this term is called molar concentration of H plus ion. This term is called molar concentration of A minus ion. This term is the molar concentration of acid Ha. Imply that I can write concentration of H plus equal to K into concentration of Ha divided by concentration of A minus. Suppose this is your equation 1. Similarly, salt Ab undergoes dissociation, gives A minus plus B plus. Since the salt Ab is a strong salt, so it undergoes completely dissociation. On the other hand, Ha is a weak acid, so it does not undergoes completely dissociation. In case of salt Ab undergoes completely dissociation, so we can write here concentration of Ab equal to concentration of A minus equal to concentration of B plus. But in case of Ha, we cannot write concentration of Ha equal to concentration of H plus equal to concentration of A minus, because the acid Ha is a weak acid, it does not undergoes completely dissociation. Suppose take this acidic buffer solution in a beaker. Here the H plus ion, A minus ion, B plus and some undissociated Ha are present. Here Ha is the weak acid, it does not undergoes complete dissociation. On the other hand, if I will think about the salt Ab, when I add the salt Ab with the weak acid Ha, then what will happen? Due to dissociation of Ab, the concentration of A minus ion goes on increases. If I will think about the Lee-Chatelier principle, now apply the Lee-Chatelier principle here. When the salt Ab is added with the Ha, then what will happen? The concentration of A minus ion goes on increases due to the complete dissociation of Ab. Because here Ab gives A minus plus B plus, here A minus is the common ion. As a result, the concentration of A minus ion goes on increases after the addition of salt Ab with the weak acid Ha. Initially Ha does not undergo complete dissociation. After the addition of Ab salt, due to increase of the A minus ion concentration, the dissociation of Ha again further suppressed due to increase in the concentration of the product. According to the Nitrile Principle, if the concentration of the product goes and increases, then the reaction, that means the direction of equilibrium shift in the backward direction. Look at that, here A minus ion is the common ion. Here the concentration of A minus ion increases due to the addition of salt AB. As a result, we think that the concentration of the product goes and increases. That's why the direction of equilibrium shift in the backward direction, which causes suppression of the dissociation of HA. So we can think that since AB salt is completely ionized and the dissociation of weak acid, HA is further suppressed in the presence of A minus ion, which act as a common ion. So in case of salt AB, we can write concentration of AB equal to concentration of A minus equal to concentration of B plus, which is equal to concentration of the salt, because your AB is the salt. In case of HA, I can write concentration of HA equal to concentration of acid, because HA does not undergo dissociation. It undergoes dissociation slightly. So we can think that there is no dissociation of HA. That means there is no formation of A minus and H plus ion. So in case of acid, HA, I can write concentration of HA equal to concentration of acid. Suppose these two equations are said to be equation 2. From equation 1 and 2, I can write concentration of H plus equal to K into concentration of acid divided by concentration of salt. Suppose this is your equation 3. Now take negative logarithm on both sides of equation 3. Then I can write minus log of H plus ion concentration equal to minus log of K into concentration of acid divided by concentration of salt. We know that pH equal to minus log of H plus ion concentration. So here I can write pH equal to minus log of K minus log of concentration of acid divided by concentration of salt. Imply that I can write pH equal to, look at that, here minus log K is present. We know that minus log of K equal to P to the power K. Imply that I can write plus log of concentration of salt divided by concentration of acid. This is called Henderson equation for acidic buffer solution. By this equation, we can able to solve many problems related to the acidic buffer solution. Next, I want to explain about the Henderson equation for basic buffer solution. Basic buffer solution means it is the equimolar mixture of weak base and its salt of strong acid. Let us consider a basic buffer solution. Suppose the basic buffer solution is made by weak base BOH and its salt, that is your BA. Here BOH is the weak base and BA is its salt of strong acid. When weak base BOH undergoes dissociation, then it gives B plus OH minus. Now applying the law of chemical equilibrium. According to law of chemical equilibrium, I can write Kp equal to concentration of B plus into concentration of OH minus divided by concentration of BOH. Here Kb is the equilibrium constant for base. This term is called molar concentration of B plus ion. This term is called molar concentration of OH minus ion. This term is called molar concentration of BOH. Imply that here I can write concentration of OH minus equal to Kb into molar concentration of BOH divided by molar concentration of B plus. Suppose this is taken as equation 1. Again we know that the salt Ba undergoes dissociation, gives a B plus and A minus ion. Since Ba salt is completely ionized and the dissociation of BOH, that is your weak base, is further suppressed in the presence of B plus ion, which is common to both this equation. By the application of Nitrile Principle, we can think that here BOH do not undergo ionization. That means here I can write concentration of BOH equal to concentration of base. Here I can write concentration of Ba equal to concentration of B plus equal to concentration of A minus equal to concentration of salt. Both these two relations suppose consider as equation 2. From equation 1 and 2 I can write here concentration of OH minus ion equal to Kp into concentration of base divided by concentration of salt. Now apply negative logarithm on both sides. Suppose this is your equation 3. So here I can write now apply negative logarithm on both sides of equation 3. Then I can write minus log of OH minus ion equal to minus log of Kp into molar concentration of base divided by molar concentration of salt. Imply that I can write here POH equal to minus log Kp minus log of base concentration divided by concentration of salt. Imply that I can write POH equal to P Kp, because we know that minus log of Kp equal to P Kp. Here I can write plus log of salt concentration divided by concentration of base. We know that pH plus POH equal to 14. Now here I can write 14 minus pH equal to pKb plus log of concentration of salt divided by concentration of base. Imply that I can write pH equal to 14 minus pKb minus log of concentration of salt divided by concentration of base. This is the Henderson equation for basic buffer solution. Now I want to do a problem related to the Henderson equation. What is the pH of the solution when 0.2 mole of hydrochloric acid is added to 1 liter of of a solution containing 1 m acetic acid and acetate ion. Assume that the volume is 1 liter. Here the K value is given. The K value for acetic acid is 1.8 into 10 to the minus 5. According to the question, look at that. Here a solution is present. The solution having 1 m acetate ion, that means 1 m CH3CO minus 1 m acetic acid, also here I can write 1 m CH3COH. According to the question, what is the pH of the solution when 0.2 mole of hydrochloric acid is added to 1 liter of a solution containing 1 m acetate ion and 1 m acetic acid? That means it is bound to add 0.2 mole of HCl to this solution. When we add 0.2 mole of HCl solution, then what will happen? HCl gives 0.2 mole of H plus ion and also 0.2 mole of Cl minus ion. That added H plus ion will combine with the 1 m acetate ion to form acetic acid. That means after the addition of 0.2 mole of H plus ion, the concentration of acetate ion undergoes change. That means here the concentration of acetate ion goes on decreases. So here I can write concentration of acetate ion equal to 1 minus 0.2 equal to 0.8 mole per liter. On the other hand, the concentration of acetic acid goes on increases. So here I can write concentration of acetic acid equal to 1 plus 0.2, which is equal to 1.2 mole per liter. Look at that, it is an acidic buffer solution. So it is bound to apply the Henderson equation for acidic buffer solution. According to the Henderson equation for acidic buffer solution, we know that pH equal to log of concentration of salt divided by concentration of acid minus log K. Look at that, here acetate ion is considered as concentration of salt and here acetic acid is considered as concentration of acid. We know that the K value for acetic acid is 1.8 into 10 to the minus 5. Now put the value of K and concentration of acid and concentration of salt in this equation, then I can write pH equal to log of 0.8 divided by 1.2 minus log of 1.8 into 10 to the minus 5. After solving this equation, I can write your pH equal to 4.5787. In our question, find out the pH value. So the pH value is 4.5787. Next, I want to explain about the hydrolysis of salt. What is the meaning of hydrolysis of salt? Suppose take a beaker. In this beaker, suppose take few amount of salt. Now add few ml of water to this salt. Then what will happen? Water gives a H plus ion and OH minus ion. The salt also gives a two oppositely charged ions. When water added with the salt, then what will happen? the ions of the salt interact with the opposite charged ions of water. As a result, what will happen? An acidic solution, or maybe a basic solution, or maybe a neutral solution will be formed. Suppose take NaCl, then what will happen? NaCl gives Na plus Cl minus ion. When water added with the sodium chloride, then what will happen? OH minus ion of water interact with the Na plus ion of NaCl. On the other hand, simultaneously H plus ion of water interact with the Cl minus ion of NaCl. This interaction is called hydrolysis of salt. So I can define the hydrolysis of salt like this. It is defined as the interaction of ions of salt with the oppositely charged ions of water to give acidic or basic or neutral solution. Let us consider hydrolysis of a salt. Suppose I will take a salt MX. That means let us consider hydrolysis of MX salt. When MX undergoes hydrolysis, then what will happen? Here MOH and HX are formed. Now apply the law of chemical equilibrium. By applying law of chemical equilibrium, here I can write K equal to molar concentration of MOH into molar concentration of HX divided by molar concentration of MX into molar concentration of water. Imply that here I can write K into molar concentration of water equal to molar concentration of MOH into molar concentration of HX divided by molar concentration of MX. We know that water is taken in excess amount in a solution. So remember, your concentration of water is constant. Now I can write here like this: K into constant equal to molar concentration of MOH into molar concentration of HX divided by molar concentration of MX. Imply that here I can write KH equal to molar concentration of MOH into molar concentration of HX divided by molar concentration of MX. Here KH equal to K into constant and KH is said to be hydrolysis constant. We know that degree of ionization alpha is equal to total number of salt undergoes dissociation divided by total number of salt taken for dissociation. Like degree of dissociation alpha, we can also think about the degree of hydrolysis H. Here H is the degree of hydrolysis. Mathematically I can write H equal to number of moles of salt hydrolyzed divided by total number of moles of salt dissolved. That means I can define the degree of hydrolysis like this. The extent of hydrolysis of a salt is known as degree of hydrolysis. The degree of hydrolysis is similar with the degree of ionization or degree of dissociation. From this mathematical expression, the degree of hydrolysis also defined like this: the fraction of total salt that get hydrolyzed at equilibrium is also called degree of hydrolysis. Now I want to explain about the hydrolysis of different types of salts. Before going to hydrolysis of different type of salt, I want to explain something regarding about the different types of salt. There are different types of salt. Such as number one is salt of strong acid and strong base. That means such type of salts are generally made by the reaction of strong acid and strong base. Let us consider an example of salt of strong acid and strong base. Suppose I want to take a strong acid, that is your HCl. When it is subjected to reaction with the strong base, suppose I will take sodium hydroxide, then a salt is formed. The name of the salt is your NaCl, and here also water is formed. Your NaCl is prepared from strong acid HCl and also by the help of strong base sodium hydroxide. So NaCl belongs to a salt of strong acid and strong base. Like that, you can also think about the other example of salt of strong acid and strong base. These are Na, NO3, Na2, SO4. These are the examples of salt of strong acid and strong base because these are formed by the reaction of strong acid and strong base. Here Na3 is formed from the strong acid, that is HNO3, and also strong base sodium hydroxide. Like that, here Na2SO4 also formed from the strong acid, that is your H2SO4, and the strong base, that is your sodium hydroxide. By the help of any strong acid and strong base, we can able to form such type of salt, that is your salt of strong acid and strong base. Like salt of strong acid and strong base, there are also other types of salt. Let me explain other type of salt, like salt of strong acid and weak base. NH4Cl is a salt of strong acid and weak base because it is made from the strong acid HCl and weak base NH4OH. This is an example of salt of strong acid and weak base. Another type of salt is salt of weak acid and strong base. CH3CONa is an example of salt of weak acid and strong base because CH3CONa is made from the weak acid, that is your CH3COH, that is your acetic acid, and from strong base, that is your sodium hydroxide. Similarly, take another type of salt, that is your salt of weak acid and weak base. CH3CONH4 is an example of salt of weak acid and weak base because it is made by from the weak acid, that is your CH3COH, that is your acetic acid, and also from weak base, that is your ammonium hydroxide. These are different types of salt. At first, I want to explain about the hydrolysis of salt of strong acid and strong base. There are many examples of salt of strong acid and strong base. The examples are sodium chloride, potassium nitrate, etc. Suppose I want to think about the hydrolysis of sodium chloride. When sodium chloride undergoes dissociation, then it gives the Na plus Cl minus ion. When we add water to this salt, then what happens? Water also undergoes dissociation, gives H plus and OH minus ion. We know that hydrolysis means interaction of the ions of the salt with the opposite ions of the water. That means here an interaction takes place between opposite ions. There are many choices for the interaction. Here H plus ion interact with the Cl minus ion and wants to form the acid HCl. But we know that HCl is a strong acid, so HCl again undergoes dissociation, gives H plus ion and Cl minus ion. Finally, we concluded that if H plus ion combine with Cl minus ion, then HCl is formed. And we know that HCl is a strong acid, so HCl again undergoes dissociation, gives H plus ion and Cl minus ion. So your H plus ion do not interact with the Cl minus ion. Similarly, if OH minus ion wants to interact with the Na plus ion, then sodium hydroxide is formed. Sodium hydroxide is also a strong base. Again, the formed sodium hydroxide undergoes dissociation, gives Na plus OH minus ion. Finally, we concluded that here also OH minus ion do not want to interact with the Na plus ion. If I will interact the H plus ion with the OH minus ion, then what will happen? Water is formed. Water is a weak electrolyte. Once water is formed, then the formed water does not undergo dissociation again. Remember an important point: if any strong acid or base is formed, then the strong acid or base undergoes again dissociation and gives the ions. On the other hand, the weak acid, weak base does not undergo further dissociation. That means finally here I can write Na plus Cl minus plus water. These are the species formed after hydrolysis of NaCl. Look at that. In this type of solution, H plus ion and OH minus ion are absent. So such type of solution are neutral. And the pH of the solution is 7. That means here I can write pH equal to 7, which is equal to 1 by 2 pKw. Here pKw is equal to minus log of Kw. This is the hydrolysis of salt of strong acid and strong base. Finally, we concluded that when a salt of strong acid and strong base undergoes hydrolysis, then a neutral solution is formed whose pH equal to 7. Next, I want to explain about the hydrolysis of salt of strong acid and weak base. There are many examples of salt of strong acid and weak base. The examples are ammonium chloride. Next is copper sulfate. Next is silver nitrate. Next is ferric chloride. Next is zinc chloride. These are some examples of salt of strong acid and weak base. Suppose I want to think about the hydrolysis of ammonium chloride. When ammonium chloride undergoes dissociation, then it gives a NH4 plus Cl minus ion. When water is added with the NH4Cl, then what will happen? Water also undergoes ionization, gives a H plus and OH minus ion. This is a reversible reaction. Finally, at the solution, these ions are present. We know that hydrolysis means interaction of the ions of the salt with the opposite ions of the water. So here H plus ion interact with the Cl minus ion. then what will happen here? HCl is formed. HCl is a strong acid, so the formed HCl again undergoes dissociation, gives H plus ion and Cl minus ion. Finally, we concluded that your H plus ion do not interact with the Cl minus ion. If OH minus ion interact with the NH4 plus ion, then ammonium hydroxide is formed. It is a weak base. That means such type of base do not undergo further dissociation. So finally we concluded that here NH4OH is formed, and the remains species are H plus Cl minus ion. Look at that. Here free H plus ion is present in this solution. So the solution shows acidic character. That means we concluded that on hydrolysis of salt of strong acid and weak base, an acidic solution is formed, and the pH of such type of acidic solution is calculated by the formula, that is pH equal to 7 minus 1 by 2 pKb minus half log C. This is the formula for the calculation of pH of such type of acidic solution. Next, I want to explain about the hydrolysis of salt of weak acid and strong base. There are many examples of salt of weak acid and strong base. The examples are sodium acetate, next is your sodium carbonate, next is your potassium cyanide. These are the examples of salt of weak acid and strong base. Among the examples, suppose I want to think about the hydrolysis of sodium acetate. The formula of sodium acetate is CH3CONa. When CH3CONa undergoes dissociation, then it gives acetate ion, that is CH3CO minus, and also it gives Na plus ion. When water will be added with this salt, then what will happen? Water also undergoes dissociation, gives H plus and OH minus ion. Hydrolysis means interaction of the ions of the salt with the opposite ions of the water. That means here H plus ion interact with the acetate ion. As a result, acetic acid is formed. Acetic acid is a weak acid, so it does not undergo further dissociation. That means here the resultant species is CH3COH. Similarly, OH minus ion interact with the Na plus ion. As a result, sodium hydroxide is formed. Sodium hydroxide is a strong base. So sodium hydroxide again undergoes further dissociation, gives Na plus and OH minus ion. Finally, we concluded that on hydrolysis of sodium acetate, we can able to find out such type of species. The species are CH3COH, another is your Na plus, another is OH minus ion. Look at that, your pre-OH minus ion is formed. As a result, such type of solution shows basic character, and the pH of this type of solution is always greater than 7. For the calculation of pH of such type of solution, we generally use a formula, that is pH equal to 7 plus 1 by 2 pK plus 1 by 2 log C. This is the formula for the calculation of pH of such type of solution. Next, I want to explain about the hydrolysis of salt of weak is your NH4, that is your ammonium acetate. Next is your calcium oxalate. Next is your ammonium carbonate. Next is your ammonium benzoate. These are the examples of salt of weak acid and weak base. Among these examples, suppose I want to think about the hydrolysis of ammonium acetate. When ammonium acetate undergoes dissociation, then it gives a acetate ion and ammonium ion. When I will add the water molecule with this salt, then water also undergoes dissociation, gives a H plus and OH minus ion. Hydrolysis means the interaction of the ions of the salt with the opposite ions of the water. That means your H plus ion interact with the acetate ion, gives the acetic acid. Acetic acid is a weak acid, so it does not undergo further dissociation. Similarly, on the other hand, OH minus ion interact with the NH4 plus ion. As a result, ammonium hydroxide is formed. This is also a weak base. So this weak base again does not undergo further dissociation. That means the resultant species are CH3COH and another is NH4OH. The nature of such type of solution depends upon the strength of these two species. If the strength of this acid is more than this base, then the solution is said to be acidic. If the strength of this base is more than the strength of this acid, then the solution is said to be basic in nature. If both the species having same strength, then the solution is said to be neutral. For the calculation of pH of such type of solution, generally we use the formula, that is pH equal to 1 by 2 of pKw plus pKa minus pKb, or here I can write pH equal to 7 plus 1 by 2 pKa minus 1 by 2 pKb. These are the formula for the calculation of pH of such type of solution. This is all about the hydrolysis of different